Let's talk about some library routines that are available for you for programming the PIC24 ADC. This configuration function right here configures for internal ADC clock. It uses manual sampling followed by an automatic conversion, and it allows the user to select some input to be sampled, either AN0, AN1, AN2, etc. It uses the two pins AVDD and AVSS as the voltage references. So this is VREF positive, this is VREF minus. That means that the voltage that's going to be converted needs to be between the voltage on this pin and ground. This parameter here, auto sample time, allows you to set the number of clocks that's going to be used to sample the input voltage. And this parameter right here will allow you to either choose 12-bit mode or 10-bit mode. Once you've called the function in the previous slide to configure the ADC, you can call this function to actually do a conversion. This macro here starts sampling. Once sampling is done, it automatically does the conversion. This macro right here waits until the conversion is finished. Once the conversion is finished, the value that's in this special function register here is returned for this function return value. This value will either be a 10 or 12-bit value depending upon how you configured the ADC using the function on the previous slide. To illustrate the use of these library functions for the PIC24 ADC, we're going to experiment with the following setup. We're going to have the PIC24 read a voltage that's present on this AN0 pin, convert that to a digital code, send that digital code via the SPI bus to an external digital to analog converter that's called the MAX548, and have this DAC convert that back to a voltage value. In order to do this experiment, we need some easy way of changing the voltage on this pin to the PIC24. To do that, we're going to use a device called an analog potentiometer. An analog potentiometer is essentially a variable resistor. It has three terminals. One terminal is going to be tied, we're going to tie to VDD. The other terminal we're going to tie to ground. This third terminal, which is called the wiper terminal, is going to be used to tie to the PIC24 ADC input. As we change this resistance, the voltage on this terminal is going to vary between VDD and ground. An analog potentiometer generally has some mechanical mechanism on it for changing this resistance. It can be a shaft, it can be a turn screw. There are various ways to do that. The MAX548 is a digital to analog converter that has a SPI port interface. It has a low true chip select line, has an S clock line as all SPI devices has, and it's a write-only device, so it only has a serial data in pin. Once it's done a conversion, the voltage appears on the out A pin. This is an 8-bit DAC, and the output voltage is going to range between ground and VDD. To do a conversion, you have to send 2 bytes over the SPI bus. The first byte is a command byte that says to do a conversion. The second byte is the byte to be converted. The command byte to do a conversion is the value 9. This byte value here is the value to be converted to a voltage, and it will vary between 0 and 255. To write a byte to the DAC to be converted, all we're going to do is we're going to enable this chip select. In our example, we're going to have RB8 tied to the chip select of the DAC, and it's a low true chip select. So this macro slave enable will bring the RB8 output to a low, enabling the device. Then we'll use the IO master SPI function to write a 9 to the DAC. We'll then write the value to be converted, which is actually passed in as a parameter to this write DAC function. And then we'll disable the DAC by bringing its chip select line back to a 1. So our sample code will first configure our IO functions. The first thing we're going to do is we're going to configure AN0 as an analog pin. This simply ensures that this pin is going to function as an analog pin and not as a digital pin. Then we'll do a configure of the ADC module. We'll choose AN0. We'll select 31 clocks as the maximum value for sampling the input. We'll use a 1 here for this third parameter. That will select 12-bit mode. A value 0 will select 10-bit mode. In order to configure the DAC, we first configure the SPI interface. Then we call the config DAC function, which basically all it does is it configures the parallel I/O pin that we're using for the chip chip select line. So this configures as an output, and then slave disable will set it to a high, which will disable the DAC. At that point, we're going to a loop, and we're first going to read the ADC value. We're going to store that in this variable called U16 ADC val. We then want to convert this 12-bit value to an 8-bit value that we're going to want to write to the DAC. We do this by shifting it to the right by 4. That's going to throw away the 4 least significant bits, leaving us with the 8 most significant bits that we're going to then use to write to the DAC. At that point, we'll write that value to the DAC. After this function is finished, what should happen is that the DAC voltage should be about the same as what was converted by the ADC. These two statements right here convert the ADC code that we got from the PIC24 ADC. It's going to convert that to a voltage. We first copy that to a floating point variable. We then divide that by 2 to the 12th, which is 4096. Multiply that by VREF. This is defined to be 3.3 in our code, and that will give us a floating point variable that's going to represent the voltage that we read from the ADC. We're then going to do the same thing for the DAC value. We take the DAC code, we divide it by 2 to the 8th or 256, multiply that by VREF, and we get a floating point value for the DAC. We then use a formatted print statement to print out these voltages. Here, this is going to print out the ADC voltage as a volt. We'll also print out the raw ADC code. We'll also print out the DAC voltage, and we'll also print out the raw DAC code in hex. We'll then delay 300 milliseconds because we want to wait a little while between samples, and then we'll go back here and do the whole thing over again. So this loop, to summarize, is simply reading the ADC value, converting a voltage on the PIC24 pin to a code by using the PIC24 ADC. We then converting that 12-bit code to an 8-bit code and writing it out to the DAC. And so the DAC voltage should be about the same as this voltage. And then we do some computations so that we can print out that DAC code and the ADC code as voltages. Here's the sample output from the program. Here's the ADC voltage and the raw ADC code. This is the 12-bit code. Here's the converted DAC voltage, and it's 8-bit code. The only difference between this DAC code and this 12-bit code is that we've dropped off the 4 least significant bits. The previous example illustrated using PIC24 code to take the PIC24 ADC, use it to convert a voltage on a pin to a binary code. In practice, you're generally going to use that ADC with a sensor that's going to take some real-world quantity and map that real-world quantity into a voltage. So looking at it, it could be, we'd say y is equal to f of x, where this is x is the real-world quantity and y is the voltage. The function that's going to map the real-world quantity to voltage can either be linear or nonlinear. A linear function is characterized by this well-known equation, y is equal to m times x plus b, where m is the slope of the line, this is the y-intercept, or in terms of these quantities up here, voltage will equal to the slope of the line times the real-world quantity plus some offset. As an example, consider an LM60 temperature sensor that produces 6.25 millivolts for every degree centigrade and has a DC offset of 424 millivolts. So the voltage in millivolts is equal to 6.25 millivolts times the temperature in Celsius plus 424 millivolts. A typical question might be, using a 10-bit ADC with VREF equal to 3.3 volts, what is the ADC code value for a temperature of minus 10 Celsius? We'll first do this in 2 steps. The first step would be to convert the temperature to a voltage. So the voltage in millivolts will equal to 6.25 millivolts times minus 10 plus 424 millivolts is equal to 361.5 millivolts or 0.3615 volts. We will now convert that voltage to an ADC code. We know that formula is Vn divided by Vref times 2 to the n. So we have 0.3615 volts divided by 3.3 volts times 2 to the 10th. It's going to equal to 112.17, which will truncate to just the final answer of 112. Many times, CPU time is a precious commodity on a microcontroller. We can reduce the number of computations from the previous slide by simplifying the equation by combining steps. So given our same question, here's how we're going to approach it. We're going to write our voltage equation, which is going to equal to 6.25 millivolts times T Celsius plus 424 millivolts, and then go ahead and directly write this as an ADC code by dividing that by 3.3 volts times 1024. We're going to multiply 1024 by these constants. Our equation will then be the ADC code is equal to 6.4 times T Celsius plus 434.176 divided by 3.3 volts. So now we have fewer computations and we have only one equation. We plug in our value of minus 10 into this equation. We get the ADC code of 112. Let's take a look at another example. A Freescale MPX 5050 pressure sensor outputs 0.2 volts at 0 kilopascals and has a sensitivity of 90 millivolts per kilopascal. So our equation will be voltage in millivolts is equal to 90 millivolts times the pressure in kilopascals plus the offset, which is 0.2 volts or 200 millivolts. A sample question may be a 10-bit ADC with a VREF of 3.3 volts returns a code value of 420. What pressure is being sensed by the pressure sensor? Well, again, we'll do this in two steps. We'll first convert the ADC code to a voltage. So the ADC code divided by 2 to the n times VREF will give me voltage. So 420 divided by 2 to the 10 times 3.3 volts gives me 1.354 volts. At this point, we'll convert the volts to pressure. So we need to solve this equation up here for pressure. And what we get is we get pressure is equal to voltage in millivolts minus 200 millivolts divided by 90. So plugging this value into the equation, we get 1354 millivolts minus 200 millivolts divided by 90, and we get a final answer of 12.8 kilopascals. Just like with the previous example, we could combine these two steps into one step and have an equation that would directly convert an ADC code to a pressure. We'll leave that for the viewer.